Alright, so in this tutorial we are going to provide physical proof of Kepler's third law of planetary motion. Something that Kepler himself was not able to show why it is, except for that the data suggested it. Newton used his principle of universal gravitation coupled with the laws of motion to come up with a very simple, elegant proof that not only showed a theoretical basis for Kepler's third law, but it gave very strong evidence once again that Newton's idea that the force of gravity falls off by the square of the distance was indeed valid. All right, this is a derivation you're going to want to know. You're going to use it again and again for various problems. All right, so let's start with a very simple situation. We have a star or a sun about which something orbits it, and an object orbits from some distance r. Okay, Kepler showed us already that r cubed over t squared is equal to the same number for all planets in the solar system. He just didn't know why that was, nor did he have any idea what the value of k was or what it meant. He tried to use a combination of mathematics and mysticism, didn't work out. So Newton did something very elegant. He basically said, look, if this thing's going around and around in a circle, in orbit, then it must be centripetally accelerating. So there's got to be some inward force, and that inward force, of course, is gravity. And that's our supply force. So he basically said we have a supply of force that pulls it in, F sub g, and since it's moving in a circle, there's a demand on that force, which we know is mv squared over r. Okay? So in order to translate this into what Kepler did, we just got to tweak both sides of the equation. So the force of gravity in general, according to Newton, is g times the mass of the planet in question times the mass of the star in question divided by the distance squared. And our demand is the mass of the object accelerating, namely that of the planet. We don't want to put v squared in there because we want to express it in terms of period. So we're going to transform v squared over r into an equation for period, something we did last chapter. And so I'm not going to do that again, but just tell you it's 4 pi squared r all over t squared. Okay? So if I cross, so we see that the mass of the planet cancels out, and if I cross multiply, what we get is g times the mass of the star times t squared equals 4 pi squared r cubed. And if I do one more step, and I'm going to put it up in the corner here, where I solve it in terms of Kepler, I see that r cubed over t squared, right, rearranging it, equals g times the mass of the star all over 4 pi squared. And this is a remarkable result. Okay, so we see that we got r cubed over t squared, which tells Newton he's on the right track with this r squared. We see that we get Kepler's third law, and we can understand why it's a constant, because for every planet, even though r and t might be different, g is the same for all the planets, the mass of the star is the same, and so is 4 pi squared. So that explains why we get a constant. Even better, if you know the distance of any particular planet and its period, and you know the value of g, then you can figure out the mass of the star which you're orbiting. And people realized immediately. The problem was we didn't know g at the time, or at least when Newton came out with this idea, and we already talked about it. It took about 100 years before Cavendish could experimentally determine it. So let's figure out the mass of the sun, knowing that the Earth orbits it with an r. If you go to the front of the note sheet where we have the data of the planets, you look at r for the Earth, it's 147.1. Now you look at the top, it says times 10 to the 9th meters. Its period is 1 year, which is 3.15 times 10 to the 7th seconds. Okay, so let's apply this. So if we have r cubed over t squared, so if we do 147.1 times 10 to the 9th cubed over 3.15 times 10 to the 7th squared, that's got to equal g, 6.67 times 10 to the negative 11th, I'll put units, times the mass of the sun, all over 4 pi squared. Okay? Now, I'm going to give the answer in a second, but it's really in your best interest to plug in these numbers and solve for the mass of the sun here, because it's very easy to make a mistake with your calculator. Anyway, if you do it correctly, you should get about 2 times 10 to the 30th kilograms. Okay? And so in Cavendish's time, people immediately were able to do that calculation. For the first time in history, we could mass the sun. Now you might be asking, well, how do we find the mass of the Earth? We'll get that in a second. So what I'd like you to do on your own is do the exact same problem, but use Jupiter's orbital data, or Venus's or Mars or whatever, and see if you get the same value, okay, to verify that r cubed over t squared is the same. So in question C is how do we find the mass of the Earth? Well, if you were to use Jupiter's data, you wouldn't get Jupiter's mass, you would get the mass of the sun. We use Earth's data of the orbital data, to get the mass of the sun. So when you have an object going around you, you can find your mass based on the orbital data of the things going around you. But what if I want to find the mass of the Earth? Well, it stands to reason I would need data of something orbiting the Earth. And the most likely thing to look at is going to be the moon. So what data do we need? Something about the moon. What specifically? Well, we need to know if this is the Earth and this is the moon. Okay, we need to know how far away the moon is, which is known, and we need to know the period of the moon. And so using Kepler's law for the moon around the Earth, we can get the mass of the Earth. All right, so that's an exercise maybe we'll see in homework or a quiz or a test, but it's the same idea. Now, even better, or additionally, maybe not better, is we can look at orbital motion a little bit more generally. In other words, we can now derive an equation for orbital velocity in any situation. We've already done this for an object near the surface of the Earth. We said the v has to be equal to radical gr. So the problem is g is only 9.8 at the surface of the Earth. What if we want to do it for any general situation? Okay, so we need to start fresh, and again, it's a supply and demand. When you're in an orbit, your supply is gravity, so that's big G, mass of the planet times the mass of the thing orbiting it, we'll call it a satellite, divided by r squared, and that's got to equal our demand. Our demand will leave as mv squared all over r, because we want v in our equation, this m is the satellite. So we see the mass of the satellite cancels out, and if we see that one of the r's cancels out here, so if we solve for v by taking the square root, we see that the v orbital is equal to big G times the mass of the planet, assuming you know the planet and you mass of the planet, which you'd have to find out by doing the period in our Kepler's third law again, divided by r. And we're going to take the square root of all that. Okay? So I don't expect you to memorize it, but I expect you to be able to derive it. It's a very simple derivation, supply and demand. So if we want to put a satellite at a certain distance above our atmosphere, just above it, so that it doesn't encounter any drag and no obstacles, we would plug in the numbers and let you do that on your own. So you're just doing it on here. So I want you to come into class with a value, and I'll verify it for tomorrow. It should be pretty straightforward. Now, a neat application of this, a special application of this, is something called geosynchronous orbits or geostationary orbits. You may have heard of them before, but if you don't know what they are, geo means Earth, and synchronous means in sync. Syn, S-Y-N, means same. Chronos means time. So it's an object that orbits the Earth, or orbits the Earth in time with it. In other words, it has the same period. In other words, it takes 1 day to go around the Earth, or 86,400 seconds. Okay? Now you might ask, why would we want a satellite in orbit that takes exactly 1 day? Well, if its period matches the Earth, then it will rotate with the Earth and always stay over the same spot, rather than move at a different speed in the Earth, so it has to come around and around again if we want it to be over America or some other place. In fact, GPS satellites work this way. There are roughly 25 or so GPS satellites in orbit around the Earth, but they're in geosynchronous orbit, so they're always above the same spot. So if I need to pick up a signal from 3 of them to know where I am, I don't have to wait for them to come back around above the horizon. So it's a very convenient way of picking up satellites. The neat thing about this is, since the period is given by definition, then it has to be put in a specific distance of orbit. And we can derive that using Kepler's laws, okay? So we wouldn't use this equation here because we don't necessarily know the velocity of that satellite, but we do know its period. So we want to express force and demand in terms of period. We've already done that in the problem above, so I'm going to go right to the general equation, which was basically r cubed over t squared, and there's another ways we could write it, equals g times the mass of the Earth all over 4 pi squared. Okay? Again, I don't want you just memorizing this. You should be able to derive this from centripetal force equals mv squared over r. Anyway, if we solve for r, let's rearrange this, we see that r cubed equals g times the mass of the Earth times t squared all over 4 pi squared. Okay, so I'm going to leave it to you to plug in this into here. The mass of the Earth, you can look up. That's somewhere in our notes. Heck, I'll give it to you now. Mass of the Earth is 6 times 10 to the 24th kilograms. Okay? To come up with this value of r. Now, be careful, because this is solved for r cubed. make sure you take the cube root of r and come in with an answer for tomorrow. You'll be surprised at how far away this is compared to the orbital distance we had for a normal satellite. All right, so I'll stop here for now. We'll do another derivation tomorrow, which is on the next page, based on figuring out the density of a planet based on orbital motion. But keep in mind, the three things that we've derived here all come from the same idea, that when you're in orbit, you have a force called gravity. It equals the ma, the second law of motion. We can express acceleration in terms of velocity or period, whichever you prefer for the situation, and you can do a lot of wonderful things with it. Okay, so we'll do practice with this tomorrow.